Hey guys, welcome back to CCL Biology, the channel for easy to understand biology lessons. If you're looking for help with general, AP, or college introductory biology, this is the place for you. I am your friendly bio nerd. Thank you so much for tuning into my channel. In today's video, I'm going to be talking all about carbs, carbohydrates that is. So if you want to get a better understanding of carbs, then stay tuned. While you're here, don't forget to hit the like button and comment below if you find this video to be helpful. And if you want more easy to understand biology videos, then be sure to subscribe to my channel and hit the notification bell to get updates about new videos as soon as they come out. This is part one of a two-part video on carbohydrates. So here in part one, we're going to look at the structure of simple carbs. In part two, we'll talk about the structure and function of more complex carbs. To start, what is a carbohydrate? A carbohydrate is a category of organic compounds, commonly known as sugars. The structure of a carbohydrate or carb consists mostly of carbon and hydrogen, hence the name carbohydrate. And they also have oxygen. Now, a carb can consist of a simple sugar molecule or a large chain of sugar molecules. Because they can form these long chains of sugars, carbohydrates are considered one of the 4 macromolecules. So be sure to check out my video on macromolecules to learn more about those 4. I'll put the link in the description box below. So to put it simply, a carbohydrate is a sugar. It can be a simple sugar or a complex sugar, but it's sugar nonetheless. So from a biological standpoint, you can use the word sugar and carbohydrate interchangeably, although we don't always do that in everyday life. The simplest carbohydrates are called monosaccharides, which literally means single sugar. Monosaccharides link up with each other to form those long sugar chains that we were talking about, and those are called polysaccharides. Now I'm going to relate this back to macromolecules in general. Each macromolecule has a monomer, which is an individual unit, and a polymer, which is multiple units of the macromolecule. So if we take a carbohydrate, the monomer of a carbohydrate is the monosaccharide, that single sugar. It's one individual unit of a carb. The polymer of the carbohydrate is a polysaccharide. So think about it like a pearl necklace. One individual unit would be the single pearl. That would be like the monomer of the necklace. When you put multiple pearls together on a string, you get the polymer, which would be the whole necklace. Now, carbohydrate with 2 sugar molecules bonded together is called a disaccharide. Disaccharides are considered simple sugars also. So as we go from 1 sugar unit to multiple, we go from a monosaccharide, which is a single sugar, to a disaccharide, which is 2 sugars bonded together, to a polysaccharide, which is 3 or more sugar molecules bonded together. So how do those sugar molecules connect with each other to make those long sugar chains? They join with covalent bonds. I also have a video about covalent bonds, and I'll include that link below as well. The reaction that brings 2 monosaccharides together with a covalent bond is called a dehydration synthesis reaction, and I talk about that in my macromolecules video. All right, so now that we've defined a carbohydrate in its various forms, let's get into some structure. Okay, as I said, all carbohydrates have carbon, hydrogen, and oxygen atoms in different combinations. But whatever the combination is, they usually exist in a 1:2:1 ratio. Now, what do I mean by that? For each carbon that exists in an individual carbohydrate, there are usually twice as many hydrogens as there are carbons, and just as many oxygens as there are carbons. So let's put letters to this ratio. So for every carbon, I'll use C for carbon. For every 1 carbon, we have twice as many hydrogens, so I'll put H with the 2 there. And we have the same number of oxygens as we have carbons. So here we get C1H2O1. Now, when writing chemical formulas, we don't write the number 1. It's just going to be implied unless there's some other number written there. So if I get rid of these 1s, all right, so now we get CH2O. Look at that, we just wrote a chemical formula. Now this is the empirical formula of a carbohydrate. Empirical is a word that used to trip me up in school, but it just means the fundamental, the basic, the thing upon which other things are built. So this CH2O is the basic chemical formula for a carbohydrate or sugar. The chemical formula for almost every sugar is just going to be a multiple of this formula or this ratio. For instance, we can have C3H6O3 or C5H10O5 or C32H64O32. So in each of these three examples, you can see we have equal numbers of carbons and oxygens, and we have twice as many hydrogens. So these three formulas and other chemical formulas for carbohydrates, formulas that are multiples of an empirical formula, are called molecular formulas. Okay, so let's run through that one more time. So the basic kind of bare bones formula for some type of chemical, molecule, or compound is the empirical formula. You're probably not going to actually see a molecule that has this formula. Again, what we're saying is just this is the basic. So once we actually do have real molecules, their formulas are going to be built on the empirical formula, and that is the molecular formula. Now, let's get into the fun stuff. Let's look at some examples of monosaccharides. So here I've got glyceraldehyde. Now this is a 3-carbon sugar, you see 1, 2, 3, which is called a triose sugar. And just a note, most sugars are going to have an OSE or OS suffix. Now, let's go ahead and count the other atoms that are here. So we've counted the 3 carbons. We can see that it has just as many oxygens, so 1, 2, 3. And then it has twice as many hydrogens, 1, 2, 3, 4. And since this one is H2, that means there are 2 hydrogens here, so 5 and 6. All right, so notice we've got 2 sets of these OH groups here. These are called hydroxyl groups. All right, and then here we have a carbon that is double bonded to an oxygen. That's a carbonyl group. Now I talk more about these and other chemical groups in my video about chemical groups, so I'll put that link in the description below. Now most sugars are going to have these 2 chemical groups in them, hydroxyl and carbonyl groups. So you just want to make sure that you can spot them when you're looking at a sugar molecule. So this particular carbonyl group is at the end of the carbon chain. All right, so meaning with these 3 carbons, it's at the end here. It's not like in the middle of the chain. So because it's at the end, that makes this entire sugar an aldehyde. So that's why it has the name glyceraldehyde. Now here I've got ribose. This is a 5-carbon sugar or a pentose, that pent of course being a prefix for 5. So we count our carbons, 1, 2, 3, 4, 5. And let's count the oxygens. We've got 1 here, 2, 3, 4, 5. And then hydrogens, 1, 2, 3, 4, 5, 6, 7, 8. And again, 2 hydrogens here gives us 9, 10. All right, so let's go ahead and circle those chemical groups. So we have 1, 2, 3. We've got 4 hydroxyl groups in this one. And we have our carbonyl group here. Again, that carbon double bonded to an oxygen. Now this carbonyl group is also at the end of the carbon chain, just like we saw with glyceraldehyde. So that makes ribose an aldehyde as well. All right, so I know I'm throwing out a lot of words right now, so let me slow down just a bit. So as far as chemical function, this particular molecule is an aldehyde. And again, check out my video about chemical groups to learn more about aldehydes. As far as what kind of biological compound this is a sugar or a carbohydrate, one of the macromolecules. Now, what kind of sugar is it? It's a pentose sugar because it has 5 carbons. So all at the same time, it's a carbohydrate, a pentose sugar, and an aldehyde. Okay, so these are just some images of the 2 sugar molecules that we just looked at, glyceraldehyde and ribose. So here you see the linear structure for the glyceraldehyde. Again, this is a triose, 3-carbon sugar. And here is kind of a 3D or ball and stick representation. So the black circles here are representing our carbons. We see the white circles for the 6 hydrogens and then the 3 red oxygen circles. And here's ribose. Again, here's another 3D ball and stick representation. And here we have the ring structure of ribose. Now I'm going to talk more about ring structures in just a little bit. The most common and most important sugar that we have as far as biochemistry goes is called glucose. This is also a monosaccharide. It's a single simple sugar. Now the molecular formula for glucose is C6H12O6. That means that every glucose molecule, as we can see here, has 6 carbons, 1, 2, 3, 4, 5, 6. We've got 12 hydrogens and 6 oxygens. And notice again that this is just a multiple of the empirical formula for sugar, CH2O. All right, so I'm going to draw out a glucose molecule. All right, so here is an illustration of glucose. Again, we have 1, 2, 3, 4, 5, 6 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens, and 1, 2, 3, 4, 5, 6 oxygens. So C6H12O6. This is a hexose sugar because it has 6 carbons. So hopefully by now you realize that when we're classifying sugars, you just use that Greek prefix plus "-ose." That'll tell you what type of sugar it is. So again, we've got some chemical groups here that I will circle. So we've got a good bit of hydroxyl groups. Okay, and then we have our carbonyl group here. All right, so as far as chemical groups go, we can see that glucose also is an aldehyde because the carbonyl group is at the end of the carbon chain. So why is glucose so important from a biological standpoint? Glucose is a major nutrient for cells and a primary source of energy for many organisms. I'm going to have upcoming videos about photosynthesis and cellular respiration, which are basically the building up and breaking down of glucose for energy. So glucose can also be used in organisms to build other organic molecules like proteins. So this is an essential molecule for animals, including us, people, and plants. So I'm going to say it and put it on the record, we need sugar. All right, I'm not saying we have to sit down on the couch with a tub of ice cream or keep a batch of chocolate chip cookies handy, but we as animals do need glucose to fuel our bodies. So I'll talk more about this in part 2 of this carbohydrate video. Another hexose is fructose, and this is probably another sugar that you've heard of. It has the same molecular formula as glucose, C6H12O6. And their structures are very similar, but they're not identical. So just a side note, this is an example to show that you can't always identify a sugar molecule just by looking at the molecular formula. Sometimes you have to look at the structure to know the difference because a lot of sugars have the same molecular formula. All right, so let's bring it back to glucose and fructose. So like I said before, the carbonyl group, this carbon and oxygen double bond, is at the end of the carbon chain. So that makes glucose an aldehyde. If we look at fructose, just at a quick glance, it looks almost the same as glucose. But notice this carbonyl group is internal to the carbon chain. It's not at either end. It's not down here and it's not down here. It's inside of the carbon chain. So that makes fructose a ketone, not an aldehyde. So they're not built the same. Now they're both sources of energy. They have similar function, but some organisms, like humans, for example, don't process these two sugars the same way. All right, so to talk about that a little bit, human bodies are very familiar with glucose, and our brains can send signals when we have enough glucose in our bloodstream. But we don't get those same signals with fructose, so that makes it much easier for us to consume too much of it. So I used to see these commercials. I don't really see them around anymore, which I'm glad about, but there were these commercials that used to advertise fructose, and they'd be like, oh, sugar is sugar, it's all the same. That is a lie. So again, hopefully they took those commercials off because it's false advertising, but fructose is not the same as glucose. Our bodies don't process these two sugars the same way. Now, we've been looking at these sugars in linear form, meaning their structures are in a line like this. But in real life, sugars usually exist as rings because they're more stable that way. All right, so here are glucose and fructose in ring form. All right, so let's take a look at this because it could be just a little bit hard to follow. All right, so first of all, with this shape here that looks kind of like a hexagon or almost like a pentagon with an O here instead of a corner. So the corners here are carbons. The C is just not written to make it a little simpler. But this corner here, this is telling you that there's not a carbon here, there's and oxygen. So if we count the carbons, remember looking at the corners, we've got 1 here, 2, 3, 4, 5, and then this one up here is 6. All right, if we count our hydrogens, we've got 2 here, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then if we count our oxygens, starting up here, we've got this 1, down here is 2, 3, 4, 5, 6. So we have that C6H12O6. If we move over to fructose, we can see it looks just a little bit different, pretty similar, but a little bit different. Mostly you'll kind of see a flip between the H's and the OH's. So here in glucose, sometimes we've got the, like here, you've got the hydroxyl, the OH group on top, and the hydrogen on the bottom. Here it's flipped. The hydrogen is on top here, and the hydroxyl group is on the bottom. And you see the same here. So that's not just some, drawing preference. That's showing an actual difference in how the sugar molecule is orienting itself in real life. All right, and so we can also see a difference here. We've got the hydroxyl group, and here we've got CH2 plus the hydroxyl group over here. So some differences in their chemical structure, just like how we saw if we were looking at the linear structure. Now, monosaccharides can function on their own as sources of energy. But otherwise, if they're not on their own, then they can bond to form polysaccharides. So for instance, what would happen if this glucose molecule joined with another glucose molecule? I'm going to take a second to draw that. All right, so here I've got kind of a starting skeleton for 2 glucose molecules. So just to let you know where I am, I've got the hexose structure, and then you see these lines, and that's where the hydrogen and oxygen atoms are going to come in. So I do have these 2 carbons written out here, but the rest of them, remember, are at the corners of the hexagon. So I'm not going to write those in, but let's go ahead and start filling in our hydrogen. All right, and then I'm going to put in my oxygens. All right, so here we have the 2 glucose molecules. Again, you see the carbons, hydrogens, and oxygens. Notice here in this corner, we've got oxygen here. So just hopefully this is a little clearer, but this oxygen is not attached to this hydrogen. So this hydrogen is coming off of this carbon. This oxygen is actually here in the ring. All right, same here. So if I have these 2 glucose molecules and they wanted to join together to form a disaccharide, then they would need to do that with a dehydration synthesis reaction. So I talk about that in my macromolecule video, but essentially what's going to happen is that one glucose molecule will need to lose an OH, a hydroxyl group, and the other will need to lose a hydrogen. All right, so that's going to happen right here where the 2 molecules are closest together. So I am going to show what happens when one loses the hydroxyl group and one loses the hydrogen. So before I do that, I'm going to take away this OH here, this hydroxyl group, and then I'm going to take away this hydrogen. So what's going to be left is the oxygen. All right, so now as we can see, these 2 glucose molecules are now joined together. We've got this oxygen here. These hydrogens are still coming off of the carbon. So let me draw that line back in. I know it's starting to look a little goofy. Now we have a disaccharide, and this particular disaccharide is called maltose. The covalent bond that's joining these 2 glucose molecules together to make this maltose right here is called a glycosidic linkage. So anytime 2 monosaccharides are joined together, the bond between them is a glycosidic linkage. The reaction that brought them together is a dehydration reaction, but the name of the actual covalent bond or the linkage is a glycosidic linkage. Well, that's it for today's video. I hope it was helpful for you. If so, don't forget to put a thumbs up in the comments section below. And if you have any remaining questions, please type those in the comment section and I'll do my best to provide you with an answer. Thanks again so much for watching CCL Biology, that is Christ-Centered Life. God bless and bye-bye.